Okay. All right. If I can get your attention up, friends, we're going to get started. We're going to do a quick review of complex numbers. Remember that complex numbers involve imaginary pieces, and we know that the imaginary number I pops up anytime we have the square root of a negative number. I is the square root of -1. Yeah. If I have the square root of a negative number, I take the square root of the number and slap an I onto the answer, because the negative sign becomes an I. Yeah. Complex numbers have two pieces. Complex numbers have a real piece and an imaginary piece. Z equals x plus I, y. Z is typically used to describe complex numbers. The x piece is the real piece of the complex number. The y piece is the imaginary part of the real number, or the complex number. Ooh, I can't spell today. Imaginary. And we can represent imaginary numbers as points in the complex plane. And the complex plane looks exactly like the regular coordinate plane. It has a y-axis, it has an x-axis, except now it's not real number x, real number y, it's real number x, imaginary number iy. So the real piece goes on the x-axis, the imaginary piece goes on the y. So, for example, if I wanted to plot the point z equals 3 minus 2i, I know the real number, the thing that doesn't have the I, is the x piece. The number in front of the y is the y piece. The number in front of the I is the y piece. Words are hard today. And so I plot it just like I would any other ordered pair in a coordinate system. So in my coordinate plane, I'm going to go forward 3, 1, 2, 3, and then down 2, 1, 2. So that complex number is sitting in the fourth quadrant. Yeah. Positive x, negative y. And we learned earlier in chapter 8 that I can describe points as an x piece and a y piece. We call those Cartesian or rectangular coordinates. But I can also describe that same number as a distance from the origin, r, and an angle from the positive x, theta. And what we're going to talk about today is how to move between them, and it's going to look very familiar. Yeah? So we'll start with polar form. I have a complex number x plus iy. I want to convert it to polar form. To do that, we're going to use what we know about converting coordinates. If I wanted to convert the point x comma y into r comma theta, what two replacements would I have to make for x and y? If it helps, we can go back to our picture and look at that right triangle. Looking at that picture, if I want to rewrite x in terms of r and theta, which trig function would I use? Tan. Ooh, if I wrote tan, tan is x and y, which doesn't introduce an r. It just changes an x into a y, which is less helpful. That's okay. So which trig function involves the hypotenuse r and my x coordinate? Cosine, yeah. X is r, ooh, that shouldn't be in blue. X is r cosine theta. Because cosine theta is x over r, yeah. Takes my rectangular coordinate, turns it into polar, r and theta. Good. Which trig function do I want for y? Sine. Y is always sine. Yeah, good. R sine theta. We're just going to make that substitution directly in to that complex number. So I have z equals, and where I had x before, now I have r cos theta plus, and then I have an I, and then y becomes r sine theta. Just replacing, right? Replacing x and y with r and theta. And you could leave it like that, and that would be correct. Mathematicians usually make it a little bit prettier. What do both of those terms have in common? R. Let's factor an r out in front. Yeah. If I pull an r out of the first term, I get cos theta plus I times sine theta. Yeah. And this, yay, is polar form of a complex number. There are two new words that are going to pop up when we talk about the polar form of a complex number. The distance from the origin, r, is called the modulus. So r is the modulus. The angle, theta, is called the argument. And Some of what you're going to see on your Delta Math this week, on your homework, is they're going to give you a complex number in rectangular form, x plus iy, 3 plus 4i, yeah, and ask you to find the modulus and the argument. So the most common thing that's going to happen is I want to go from rectangular to polar, meaning I need to know how to find r and theta if I'm given x and y. So that's the skill that we're going to practice today. As a little side note, you will sometimes see this big ugly thing, r times cos theta plus I sine theta, written as r cis theta, where cis is cos I sine. You won't see that on Delta Math. Delta Math is going to use this formula, yeah. But your textbook will sometimes write it like this, and mathematicians know that that means cosine I sine. So this is shorthand for that. And we like shorthand, right? Mathematicians are lazy. All right, let's practice going from rectangular to polar. And practice finding our modulus, distance from the origin, and our argument, theta, angle from the positive x. And just like rewriting those complex numbers in polar form involved pooling our knowledge of converting between the two, this is also going to do the same thing. If I have a complex number z plus, or z equals, come on, eraser, there we go, x plus iy, how do I find r and theta? So I'll draw a picture off to the side so we can get a visual. Familiar picture. I have a point in the complex plane with an x-coordinate and a y-coordinate, x, y. I want to use that x and y coordinate to find r and theta. So first question, I have a right triangle. I have the legs of the right triangle. How do I find the hypotenuse r? Starts with a P. We have a limited number of theorems that apply to right triangles. It is louder, Daniel. Exactly, gold star Daniel. Pythagorean theorem. A squared plus b squared equals c squared. In this case, x squared plus y squared equals r squared. So r is the square root of x squared plus y squared. And we saw that last week when we talked about converting between polar and rectangular coordinates. Yeah. For theta, you have a couple of choices. So you can set up cos. Cosine is x over r. You can set up, if my pen would work, sine theta equals y over r. You can set up tan theta equals y over x, opposite over adjacent. Yeah. So you're going to pick one of those trig functions, right? I don't have to do all of them. They should give me the same answer. So let's say I go with cosine. Cosine equals x over r. I don't want cosine of theta. I want theta. How do I undo cosine? Cos inverse. Very good. So you set up the trig ratio that you want to use, and then you do the inverse trig function to get at the angle buried inside it. Good. Just like we did converting coordinates in the real plane. Yeah? All right. Do some examples. Give you time to start your homework. Yeah? For those two dings, we have two people out. You need to wait till they come back. All right, first example, we're given the complex number z equals 3 minus 4i. And I want to find r and theta, its modulus and its argument. Yeah. And my instinct is I'm going to quickly sketch what that point looks like in the coordinate plane, so I have a visual, because I know that's going to help me with interpreting my angle when I go to find that argument theta. So really quick off to the sky, we're going to do a quick sketch. I want to go 1, 2, 3 over and down 4, 1, 2, 3, 4, so I'm right here. So this is 3, this is 4. I want theta and r. The nice thing is we have equations for that now. To find r, we're just going to grab that reformatted Pythagorean theorem. R is the square root of x squared plus y squared. And my x is positive 3. My y is negative 4. Square root of 3, 3 squared is 9. Negative 4 times negative 4 is positive 16. So this is the square root of 25, which is 5. Yeah, r equals 5. Happy face. So I found my modulus. My modulus is 5. Now I want my argument. I need to pick a trig function. Alexis, give me a trig function. Which one do you want to use? Cosine? Okay, so cosine theta. If here's my angle, it's adjacent over hypotenuse. So 3 over 5. Positive 3 over positive 5. Yeah? We okay with that? I don't see any argument. I'm going to assume I did that correctly. And in order to get theta, I have to do cos inverse. If you could do me a favor and make sure that your calculator is in degree mode. Degrees, I think, will be more helpful here. and give me an answer. What is cos inverse of 3 over 5? Omar, what did you get? Cosine inverse of 3 over 5. 53.1. So I'm going to just round to 0.1, 53.1. Good. Looking at the picture, not the number, the picture, is that positive 53.1 or negative 53.1? Negative, because it's below the x-axis. Positive angles, we start at the positive x and rotate counterclockwise. This guy went down, which is clockwise. So this, even though my calculator didn't tell me, my argument is negative 53.1, which is why I would always recommend on a sheet of scratch paper, draw the x and y, plot that point in the coordinate plane, so you have a visual, right? We want to measure from the positive x-axis. If we go counterclockwise, theta is positive, clockwise, theta is negative. Yeah? So that tells me that my original ordered pair, z equals 3 minus 4i, can also be written as z equals 5 cis negative 53.1 degrees. So 5 times cosine of negative 53.1 plus I sine negative 53.1. Modulus argument. Yeah. Process should feel exactly like it was converting between x, y, r, theta with points in the regular real xy plane. Yeah? Process is the same. Just new terminology. R is being called modulus, theta is being called argument. Process is the same. All right, I'm going to pop one more up there. I'm going to give you a couple minutes in your small group to do it, and then I'll give you some homework time. All right, I'm going to pop 4 minutes on the clock. In your small groups, finding modulus, finding argument. All right, so let's go ahead and go through this really quick. So first I'm going to draw my picture. Back 2, down 6. 1, 2, 3, 4, 5, 6. Got to go down a little further. So I'm sitting right here. Draw my picture. Here is my r. Here is my theta. This is -2. This is -6. Did I do that correctly? It's -2, +6. No, I've got it down on the wrong side. Why did nobody say anything? Just watch me do the wrong picture. You were enjoying me making a boo-boo, weren't you? Try that again. So back 2, up 1, 2, 3, 4, 5, 6. So we're right here. That looks slightly better. So -2, +6. which means this is the angle that our calculator is going to give us. It's not the angle we want. We have to think about that. All right, how do I find my modulus R? Melissa, how do I find my R value? X squared plus y squared. Very good. So we pull that from the picture. X is -2, y is +6, which means we get the square root of 4 plus 36, which is 40. And we're looking for the biggest perfect square that divides into 40. And I'm pretty sure that it's 4. 40 is 4 times 10. What is the square root of 4? 2. So I think that my R value is 2 root 10. And I'm going to leave it like that because that's an exact value. Right? If you convert it to a decimal, you're going to have a rounded decimal. Don't use sine or cos. Use tan when you go to find your angle. All right. So which trig function do I want to use here? Sam, what trig function did you use? Cos. You can use cos, yeah. Cos theta is x over r. So we get cos theta equals, and our x coordinate is -2. Our r is 2 root 10. So on my calculator, I'm going to do cos inverse of that whole thing, -2 over 2 root 10. And my calculator is in degree mode, because that's easier to deal with. Let's see what I get when I do that. So cos inverse -2 divided by 2 square root 10. And I get, when I do that, I get theta equals 108.4. Did anybody else get theta is 108.4? I see a couple nodding. Good. Is that angle right here? No, because that angle is smaller than 90. What we just found here is actually from the positive x around. That's the 108.4. And it gave us the correct quadrant because we used that negative x value. So it knew that it was in quadrant 2. It should have a bigger than 90-degree angle. Good. Very good. You have Delta Math this week. The first 2 sections of it are just practice finding modulus and argument r and theta, going back and forth between the coordinate plane x, y, and the polar plane r theta. Tomorrow we're going to start vectors. Yeah? Yay.